Welcome to your Chapter 2 bonus multiple choice review video. So in this video, we're going to look at 9. I would typically have 10 here, but one of the questions was really I didn't really think it was a very good question. So I left it off completely. But I've got all these at the back of the Chapter 2, what was it? The AP practice test, basically. It should be the very last thing in Chapter 2. So if you want to see where these problems are, they're in your book. So I'm not just pulling these out of thin air, getting them from a different source. So we will take a look at these. Now, if you want to pause the video and try this problem on your own, fast forward through the video and see what the answer is, and if it matches your answer, then don't necessarily worry about watching me explain and do the problem. If you fast forward through the video and you don't get the right answer, then rewind it back and watch the whole explanation. Or you can just watch the whole thing because maybe I did the problem a little bit differently than maybe what you have done. But remember, with the multiple choice on the test and on the AP exam, you don't have to show any work. So if you do it one way and I do it another way, then if we end up with the same answer, we both get the same amount of credit. All right, so this first problem says, many professional schools require applicants to take a standardized test. Suppose that 1,000 students take such a test. Several weeks after the test, Pete receives his score report. He got a 63, which placed him at the 73rd percentile. This means, so what we are doing basically is we will be defining the 73rd percentile in this problem. So percentile meant the percent of values less than yours, or in this case, Pete's. So Pete's score was below the median. Well, no, we know his score wasn't below the median. The median's the 50th percentile, and he's at the 73rd. So it's not it. Pete did worse than 63%. Well, just because he got a 63 on the test does not correlate to our percentile value. So anything that's got a 63% in here, we get to throw out. The 63% is how well he did on that particular test. And we're trying to compare them to the other people, which is our percentile value. So Pete did worse than 73% of test takers. Well, that's looking at the wrong way. This is looking at more of a greater than approach than a less than approach. So that leaves us with E, that Pete did better than 73% of test takers, which is the case here. So if he's at the 73rd percentile, assuming we have a normal distribution, which I don't know if we really do or not, but if he's in the 73rd percentile, there are 73% of people that did worse than him, or he did better than 73% of people. So depending on which way you want to look at it there, E is the same answer for either case. Problem 2. For the normal distribution shown, the standard deviation is closest to 0, 1, 2, 4, 5. Well, man, this is crazy. How do we do this problem? We just have a normal curve and we're supposed to get the standard deviation just from it? Well, here's how we're going to have to look at this. So the mean is in the middle. So let's draw that in. It's about at 2. Okay. And some people might instantly go, well, the standard deviation, that's 2 because look, each one of these represents a standard deviation. No, they're just counting here on the axis for you by 2's. They're just being nice. That's not necessarily how much a standard deviation is. So we mentioned in class a standard deviation is if we were up here at the peak and we were going to ski down. There are poles. Yeah, I tell how often I go skiing, which is none really. If we were going to ski down this hill, eventually we're going to hit a certain point where our velocity doesn't increase anymore. Basically, our acceleration becomes 0. So we got to find that point somewhere along the curve where we think our speed would no longer increase. So I think when we start going down, oh, we're gaining speed, we're gaining speed, we're gaining speed. And then if you notice about right in here, that's where the hill starts to come up a little bit, right? And we're going to start to slow down just a hair, or at least our acceleration is going to become 0, and we might maintain our velocity. So I would say it's somewhere in this vicinity is where the curve starts coming up just a little. And so if we go straight down from there, we're right around 6. So that is how much one standard deviation is worth. And the distance between 2 and 6 would give us a standard deviation of approximately 4. Now, I did mention in class that it's sometimes we could go about halfway on this normal curve. And that's not really halfway, is it? Let's see, let's make this a little better. I keep scooting it down. There. Maybe that's about halfway from peak to bottom here. But if we do that, again, you can still tell it's close to 6, right? So you'd still say it's about 4. So either way there, if you want to go the half route here, that's a really rough approximation. Again, you want to try to find the spot where the hill starts to not be as steep and slope. And that puts us right at about 6 there. All right, 3, rainwater collected in water collectors at 30 different sites near an industrial complex. The amount of acidity was measured. Mean and standard deviation are 4.6 and 1.1 respectively. When the pH meter was recalibrated back at the laboratory, it was found to be in error. The error can be corrected by adding 0.1 pH units to all of the values and then multiplying the result by 1.2. The mean and standard deviation of the corrected pH measurements are fill in the blank. Now, we don't have all of the data for the 30 different sites. So we can't take 0.1, add to it 0.1 to all those 30 sites, and then multiply all those results by 1.2. So we can't necessarily do that with the whole data set. But we were given the next best thing. We were given the mean and the standard deviation for those 30 sites. And so we mentioned in class that if we're going to shift our data around with adding and or multiplying, that we can just deal directly with our statistics, our mean and our standard deviation. So if it says we just want to add 0.1, well, did adding affect our mean? And it did. It just shifted it down the line. So we do want to add 0.1 to our mean. But did adding and subtracting values affect our standard deviation, our spread? And that was a no. So we don't want to add 0.1 to our standard deviation. Next, then multiply the result by 1.2. So we need to think of it's all of this times 1.2 and multiplying affected mean and multiplying affected standard deviation. So now we just need to figure out what these come out to be. So this is nothing more than 4.7, and then let's see, what's 4.7 times 1.2? I get 5.64. So just looking over here, I know it's not C or D. And then let's see, 1.1 times 1.2 is 1.32. So our answer is B. Now, if you would have added, not 0.01, but if we would have added 0.1 to get 1.2 and then multiplied that by 1.2, we would have gotten 1.44. And you better believe that's an option they're going to try to get you with. How did they get 1.2? Well, they took 1.1 and they subtracted 0.1 for some odd reason. To get 1.0 times 1.2 would give us that 1.2. All right. Number 4. The figure shows a cumulative relative frequency graph. And remember, that was just our ogive of the number of ounces of alcohol consumed per week in a sample of 150 adults. About what percent of these adults consume between 4 and 8 ounces per week? All right, so we need to know which axis are we going to be really using here. So we need to look at the context, 4 to 8 ounces. Well, we're talking about percent over here, and here's consumption. And that's what we're referring to as consumption. So 4, let me get my straight line tool here. 4 ounces would come up and hit the ogive here, and 8 ounces would come up and hit the ogive there. Now, from those points, we need to swing over and see what percentile that would put us in. So at 4 ounces, we're at the 20th percentile. At 8 ounces, we're at the 60th percentile. So how many adults would be drink between 4 and 8? Well, what is between 20 and 60%? And that would give us 40%. Ba-boom, answer choice B. Number 5, the average yearly snowfall in Chileville is normally distributed. So since this specifically says it's normally distributed, we may use our calculator commands of normal CDF and inverse norm. If it doesn't mention anything about being normally distributed, keep in mind you cannot use normal CDF or inverse norm. So we got a mean of 55 inches, and we need to figure out the standard deviation. But they tell us if the snowfall in Chileville exceeds 60 inches in 15% of the years, what is the standard deviation? All right, so let's get a picture here. Let's try to get an idea of what's going on. Because they gave us some numbers we could draw a picture for. We know the mean's 55. They mentioned 60 inches of snow, so that would be somewhere to the right. And since we don't know what a standard deviation is worth, I'm just going to stick it somewhere over here. But it says if snowfall exceeds 60 inches, then that happens in 15% of the years. So exceeding, get a little bit smaller here, exceeding 60 inches would be all of this region down here. And they're telling us that is 15%. Now, could I use normal CDF in this scenario? Well, let's see. I know a lower bound. I know an upper bound. I know a mean. Womp womp. But I don't know a standard deviation. Sad face. So, if I can't use normal CDF, whoa, way too much. Come on, give me some of that back. There we go. Oh, one more. There. Okay. We can at least use this 15%. And how can we use the 15%? We can use some inverse norm here. Now, inverse norm, remember, goes to the left. It's always below. So if this is 15% above, I would want to use inverse norm 0.85, and I'll just leave it at that for right now. So inverse norm 0.85. If you wanted to put in 55, then you would need to know the standard deviation, which you don't know. But if you didn't know the standard deviation, it would just give you that 60 back that we already know. So we just need a rough z-score here. So I'm going to leave the mean of 0 and a standard deviation of 1. I'm just going to do a standard normal distribution. So to be here at 60 inches, that means we are 1.036 standard deviations above the mean. That is our z-score. Okay. Now I need to use my z-score formula, which was z equals x, which is our individual value, minus the mean, divided by the standard deviation. We know our z-score to be 1.036. We know our individual value, x, that's the 60 in question here. The mean we know is 55, and then here's our missing piece of the puzzle, the sigma. Now, I could cross multiply here, and if I cross multiply, I'm going to get 1.036 sigma equals 5 once I subtract those. Then I'm going to divide both sides by 1.036. So 5 divided by 1.036 gives me a sigma of approximately 4.826. And what would that be closest to? Would be 4.83. Now, number 6, I'm skipping. That was the bad problem. I didn't really care for it. I thought it was a little deceiving. So to number 7 we go. If the heights of American men follow a normal distribution, so we've got something good here we can work with, and 99.7% have heights between 5 foot and 7 foot, what is your estimate of the standard deviation of the height of American men? Now, since we know we have a normal distribution, we can draw a normal curve. We don't really know what the mean is, right? Not yet anyway. But it says 99.7% have heights between 5 and 7 feet. Well, 99.7%, and they're kind of meaning, to the left and to the right, so we mean the middle 99.7. That's 3 standard deviations, above and below, so kind of plus or minus 3 standard deviations. So if I went 3 standard deviations below the mean, I'll just chop it off right here, we're saying that's 5 foot. And if we went 3 standard deviations above the mean, now we're at 7 foot. Okay, so here's 3 standard deviations down, here's 3 standard deviations above. So I think we can figure out what the mean is, right? It's in between 5 and 7 because the curve is symmetric. So the mean's got to be 6 feet. All right. Now, does that help us necessarily figure out what a standard deviation's worth? Maybe, maybe not. Depends on how you want to look at this. We can focus our attention on, let's say, the whole thing. The 3 up and the 3 down. Okay. Between 5 and 7 feet, we have 2 feet. And that goes through 6 standard deviations worth, right? 3 down and 3 up. That covers a span of 6 standard deviations. So if we want to know how much a standard deviation is worth, really I should have not put a biconditional sign there, but an equal sign. We could divide both sides by 6, and we could say a standard deviation is worth 1/3 of a foot. And a foot is made up of 12 inches, so 1/3 of 12 inches would give us 4 inches. If I can figure out how to work this thing here. 4 inches for a standard deviation, which is answer choice C. Now, we also could have, instead of looking at the whole 3 up and 3 down, we could have just looked at the right side or the left side. It really doesn't matter. So the span of here, if you understand that this needs to be 6, we have a 1 foot difference between the mean and 3 standard deviations up. So again, 1 foot represents 3 standard deviations. We can divide the 3 over. So a standard deviation is 1/3 of a foot, which is 4 inches again. Number 8. Which of the following is not correct about a standard normal distribution? So remember standard normal, that's when our mean is 0 and our standard deviation is 1. That's where all of our values on our standard normal curve are z-scores. Why does it keep doing that? It's being crazy. Okay. But they give us all these different bounds. Oh, left off my 1.5 there. There we go. And they're giving us all these areas. So they're telling us the proportion that are, in between or less than or greater than these z-scores are these certain numbers. So really all we got to do is we can just use our calculator to see which one works out here. So for the first one, let's just check it out. If z is between 0 and 1.5, so a standard normal curve means it's 0, 1.5 or 1.5 standard deviations above the mean. We'll just put it there. So they're saying this region right here is 0.4332. Well, let's see if that's true. We can just do normal CDF, lower bound 0, upper bound 1.5. And since it's a standard normal, we can just stop right there. I mean, you can put in comma 0, comma 1, but that's the kind of default values there. So normal CDF, 0 for my lower, 1.5 for my upper, and I get 0.43319, which is going to bump up to a 2. So that is a true statement, but I'm looking for a not correct statement. Okay. So to B, z is less than -1. -1 means we're 1 standard deviation below. Since we are shading, or we're saying less than, we're going to shade below this guy. So then we'd have normal CDF. Lower bound would be -infinity, all the way up to -1. We can stop it from there. So let's see, normal CDF, -99999, up to -1. Everything else stays the same, and I get 0.1587. And that's what it says there. Pooh, we still haven't found the incorrect one. All right, keep going. Need a new normal curve. Normal curve, thank you. Z is greater than 2, +2. We are 2 standard deviations above the mean, about right there. Since we are greater than, we're going to shade to the right. Switch you down just a hair. There we go. All right, so then we have, again, normal CDF, 2 to infinity. So let's see, normal CDF, 2 to 99999 gives us 0.02275, which rounds to be that number. Yes, that's still correct. At least we're down to 50-50 now, right, guys? So less than 1.5. So if this was 1, we'll call this 1.5. Less than 1.5 would be all of this over here. So hope you don't mind me kind of reusing my last normal curve here. So normal CDF, lower bound's -99999, upper bound is 1.5, and I get 0.9332. Man, are you kidding me? They leave the wrong answer to be the last problem. Now, let's just double check to make sure that it truly is the last one here. So 0 in the middle, -3 all the way down here. We are shading to the right since it's greater than, and we know, since process of elimination here, this needs to be the wrong one. So let's see how off it is here. So lower bound's -3, upper bound's 9999999. We keep 0 and 1, and I get 0.9987. So it's not that much off, but it's off by just enough that we wouldn't have been able to, been like, oh, well, that one's obviously wrong, right? Finally. All right, 9 and 10 are going to use the same pieces of information here. So 9 and 10 say, until the scale was changed in 1995, SAT scores were based on a scale set many years ago. For math scores, the mean under the old scale in the 1990s was 470 and the standard deviation was 110. In 2009, the mean was 515 and standard deviation was 116. So question 9 asks, what is the standardized score, the z-score, for a student who scored 500 on the old SAT scale? So we want a z-score, so we need to use the z-score formula here. So z equals x minus mu over sigma. This is what we're trying to figure out. Now the student, that's the individual x value here, 500. The mean on the old one was what, 470? Standard deviation was 110. So really 30 over 110, really 3/11ths. What does 3/11ths come out to be? 0.27, basically 0.27 repeating. So 0.27 repetan bar. Now, 0.27, boom, boom, boom. Oh, now is it positive or negative? Well, we got a positive answer here, so it's got to be the positive one. Plus a 500 is above the mean of 470, so we know it's got to be the positive 0.27. And the last problem. Jane took the SAT in 94 and scored a 500. Her sister Colleen took the SAT in 2009 and scored a 530. Who did better on the exam, and how can you tell? Well, they took technically two different SATs, right? Jane took the older one, which was based on a different mean and a standard deviation, then Colleen taking it more recently, which was based, again, on a different mean and standard deviation. So we need to calculate two z-scores to see how well they did on their respective exams during those respective times. So let's do the z-score for Jane. So I want to do everything here in terms of J for Jane. I don't know why I went uppercase to lowercase. Don't know. Jane scored what, a 500? Is that right? Yeah. Okay, so Jane's the one we just did, right? There's where we got the 0.27. Okay, so Jane's z-score, z sub Jane, 0.27. Now we just got to do Colleen's z-score. So she scored a 530. Her mean on her test was a 515, and her standard deviation was 116. So really we're taking, what, 15 divided by 116. What does that come out to be? 0.1293. Okay, so there's Z Colleen. So who did better? Well, Jane's z-score is higher, which means she's further away from the mean in a good way, right? She's above the mean. So she did better than more people in 1994 than Colleen did, because she was only 0.1293 standard deviations above the mean compared to the people who took her SAT in 2009. So Jane is the winner. So we know it's not A or B. The two sisters did equally well. Their z-scores are the same. No, we know that's not true. Jane's standardized score is higher than Colleen's. That's our answer, but let's look at D here. The standardized deviation was bigger in 2009. Makes no difference. So that is our final answer there. So there are the 9 problems we went through. So hopefully these will help you out in kind of preparing for the multiple choice problems on not only the chapter test we will have in class, but also the AP exam. So adios.